Let's now look at how to use Excel solver to solve for this transportation problem. So what I copy here is the algebraic model of the Carlton pharmaceutical problem, which is a transportation example. So the first row is the objective function, followed by 7 constraints. Now, here, what I have done here is simply transcribing all the constants from the algebraic model into Excel. And I tend to put a name right above where the decision variable are stored. So these 12 cells are the location where the decision variable are stored, which is where Excel is gonna populate the value to those decision variable once the problem is solved. And right below the decision variable are the constants or the coefficients associated with each decision variable. Now, in the constraints, notice the first constraint is only concerned with x sub 1, 1, 1, 2, 1, 3, and 1, 4. And the constant or the coefficient for each one of them is simply just 1. So x11 can be understood as 1 times x11. Therefore, the coefficients for this decision variable for the first constraint is actually 1. So you have 1, 1, 1, 1 here. How about these? So first constraint is not concerned with x21 or x22. It's not concerned with any of these following decision variable. So you could interpret it as, in this first constraint, the coefficient for x21 is actually 0. So you can think of this as 0 times x21. And in Excel, an empty cell means 0. So similarly, I can transcribe all the constants for the remaining constraints down here this way. And finally, I simply copy all the constant on the right-hand side in this column. And again, as we had done before, I also copy those signs to put in Excel. Again, these are just reminders for me. When I go to the solver dialog box, I need to make sure I select the right signs. So far, I have not put in any formula just yet. All I have done is simply transcribing all the constants from this algebraic model into Excel sheet. Now let's enter the formula to properly link all these information together so solver can solve for it for us. Now we have been using sum product, and here again we're going to use the same sum product function. So the first array of our sum product is going to be these empty cells we designated for storing decision variable. So I'll put a comma, and then I would select the constants for the objective function, and you can close it. And again, make sure you do understand what sum product does. As the name suggests, it's a sum of products. So where are the products? The products are these, the pair. So in this case, I need to multiply 35 by x11, 35 by x11. So the value of x11 is actually stored in this cell, D22. So I have the first product, which is this cell, D22 times 35 in D23. I would have second product, which is E22 times 30. So I would have 12 products. And then at the end, I need to sum them together because that's what the objective function is. And so that's what the sum product function does. You calculate a bunch of products and then you add them together. So you need to make sure the product, all the cells are lined up properly as you intended for them to be. And the second thing that we have done before is, since I want to be able to reuse the same formula down in the constraint part, I want to log row 22. I want to lock row 22. So all I need to do is put a $ in front of 22. Now, once you have this, I can just copy and paste the same formula for all the constraints. Now, what I would do is I would just use the PC shortcut. I would just press Control C here, and then I will select the target cells I want to copy that formula to all at one time. And then I will press Control V. And here, and then that is the quickest way to replicate the formula. And again, since we have the $, you can individually verify that the formula works. And just quickly, that for the MacBook, the shortcut is Command C and Command V for copy and paste. Now let's take a closer look at this formula and to verify or to convince yourself that this does the job that you wanted to, right? Again, this one is the first constraint on the source side. So this says x11 plus x12 plus x13 plus x14 is the left-hand side value. And let's look at what sum product does here. It pair all of them together, do the product, and then sum together. Now, as I said before, if you leave this empty, or you can put 0 there. So if I have a 0, empty means 0 in Excel. So if I have a 0 times x21, that means the x21 is going to be wiped out. And similarly, it's true for the remaining decision variable. And for these 4 decision variable, I have the constant of 1. So in this case, I would have 1 times x11, 1 times x12, 1 times x13, 1 times x14, and then I will add them together using the sum product. So that's why this setup would be able to capture these constraints. And equally, it can capture all the constraints below, because again, you are putting the right constants at the right columns. Now, so once you have all and that's really it. You just need to have that formula, one formula that is sum product to enter. And now we can go to data and solver and then make sure we select the right field so solver knows where to look for things. And our objective function is stored here. Our goal is to minimize the total shipping cost. Therefore, we select min. Our changing variable cells are this row. And now we need to input the constraints. And we can do this by, notice that because the first 3 constraints share the same signs, which are less than or equal to, I can select them all at one time. So I will need to select the left-hand side as these 3 cells. Then the sign is less than or equal to, and then I can select the right-hand side constants this way. And again, this is only feasible because these signs are identical. And then we can use the same form fraction to select the second set. Left-hand side are these 4 cells. Again, these 4 cells contains the sum product formula that we just showed before. And these 4 constraints have equal sign. And the right-hand side constraint are here. And then we just click on OK. And again, in this case, we do require variable to be non-negatives. And then this option has been pre-selected. And it's a linear programming problem, therefore a simplex LP. LP stands for linear programming, should be sufficient. And let's just click on solve. Notice that the solution has the solutions has been populated into those empty cells earlier. And we can click on answer, will produce an answer sheet, okay? And so again, notice the important part about this structure is if you set one column to store if you let one decision variable take on one column, like this way, and you use one row to capture the constants for objective function, and then you use as many rows as they are constrained, like we have just done earlier here, and you use sum product for the left-hand side. If you use this generic structure, it can handle as many decision variables as you have, as many constraints as you have. And in practice, it's not uncommon to have a optimization problem that has hundreds of decision variable and hundreds of constraints. But as you can see, once you have this format clearly understood to you, then it's really scalable, because all the formula is just simple copy and paste. And once you understand the structure clearly, you can quickly verify whether the transcription or translation from algebraic problem into Excel is done correctly if you have written an algebraic model, follow this practice.